Welcome to How AI Models Work.
And we are very glad to have you here with us today.
Yeah, today we are bringing you a plain English guide to the April 2026 articles from the HowAIModelsWork.com monthly guide.
Which is a really fascinating set of articles this month.
It really is. Our mission here is to take you through this material step by step. We want to help you clearly understand what is actively happening under the hood of these systems, the ones you are probably using every single day.
And I think if there is one central unifying idea to take away from all the articles this month, it is this. AI can produce fluent text, convincing motion, and apparent memory. But these behaviors come from prediction-based systems.
Yeah, they aren't just magic boxes doing whatever they want.
Far from it. They are always operating within strict engineering limits. Limits on context, on computation, memory, and consistency.
And we see that prediction process most clearly when we look at how these systems write. Let's start with a common experience you have probably had. You ask a system a question, it gives you a good answer, and then you ask the exact same question later. But the wording is completely different.
Or maybe the tone shifts a little or the details change.
Yeah. So if it already has the answer, why does a single prompt yield such different results?
Well, it happens because language models do not retrieve fixed, pre-written answers from some sort of database. They generate text token by token.
And a token, just to clarify, that might be a whole word or just a piece of a word.
Yes, exactly. The model is essentially looking at the text it has generated so far, and it's predicting what small piece of text should come next.
Oh, I see.
And for almost any prompt you give it, there are several plausible continuations. So the model is continuously choosing from a range of statistically likely options.
Okay, let's unpack this. Think of it like choosing a path in a branching storyline. Picking a different opening word is like opening a different door that completely changes the rest of your journey.
That is a great way to picture it. Once the model chooses that first specific token, it creates a new path that influences every single word that follows.
But if it is just looking at a menu of plausible words, there must be a way to tell it whether to play it safe or get creative. How do the generation settings specifically shift the likelihood of taking one path over another?
That brings in a setting known as temperature. Temperature adjusts the probability landscape during generation.
So a lower temperature does what exactly?
A lower temperature generally reduces variation. It pushes the model toward the most statistically likely paths.
But it doesn't force the model to always pick the absolute most likely token every single time, does it?
No, not at all. It does not always force the selection of the single most likely token. It just narrows the pool of options. A higher temperature, on the other hand, generally allows for more lower probability alternatives to be chosen.
So it sort of flattens the landscape.
Yes, which leads to more varied, diverse text.
Which explains why the same prompt can produce a highly predictable response one day and a much more unexpected one the next, just by tweaking those math settings.
Yes.
But what happens when the prompt itself is unclear? Like when you ask an ambiguous question, the system might infer a specific meaning and just run with it. Or it might stop and ask you for clarification. It doesn't just feel confused, does it?
No, there is no feeling involved. That reaction depends purely on its instructions and how the product was designed.
Okay, so it's a design choice.
Yes. If the product engineers tuned the system to prioritize engagement, it might just guess your intent and generate an answer. If they tuned it for accuracy, it might output a programmed response asking for more details.
We see something very similar with cautious wording, too. Sometimes you ask a simple question and you get this very careful, highly qualified answer layered with disclaimers.
Yeah, and when an AI gives you a very careful answer, it is not because the AI is experiencing a human feeling of caution.
It isn't getting nervous about answering wrong.
No. Nor does it prove that the model is locked into one specific probability distribution. Cautious wording is the result of instruction tuning, safety policies, or the context of your prompt.
Or maybe uncertainty cues within the model's own layers.
Yes, or strict product rules designed by the developers to prevent harm. It is just balancing the mathematical goal of answering your question with the mathematical goal of not generating unsupported claims.
Based entirely on its training. But this dynamic leads to a really dangerous illusion for the user, doesn't it?
What's fascinating here is how human readers naturally interpret smooth grammar and a steady tone as a signal of verified truth.
Oh, wow, yeah. We are socially conditioned to believe that if someone speaks clearly and confidently, they know what they're talking about.
But in AI, fluent, confident language does not prove factual accuracy.
Because it's just predicting tokens.
Yes. The system is generating a plausible sequence of words. That leads to misplaced trust when the output is perfectly written but factually flawed.
Okay, so if predicting the next word in a static paragraph is already this complex juggling act of probabilities and paths, what happens when we add time and space into the mix?
You mean with video generation?
Yeah, because watching AI video, the illusion of reality is even stronger. But the math behind it must be exponentially harder.
It is a massive leap in complexity. We're moving from predicting the next word in a sequence to predicting visual changes across space and time.
And we have to remember, AI video is generated. It's not filmed?
Yes, there is no physical camera, no set, and no real physics engine running in the background. The models create or refine visual representations across space and time, guided by your text prompt, a starting image, or maybe existing footage.
When you watch a short 2-second AI clip, it looks stunning. But as the sequence gets longer, the illusion always seems to break.
That is because maintaining characters, objects, lighting, the camera position, and the overall scene structure becomes significantly harder over longer sequences.
So every added second is just a new chance for things to go off the rails.
Yes. Every added second creates more opportunities for the scene to drift. A character's jacket might suddenly turn into medieval armor.
Or the lighting might shift from noon to sunset for no logical reason.
Exactly, because the model is trying to predict a cohesive sequence over an ever-expanding time frame.
And it isn't just generating entirely new videos from scratch either. A lot of tools offer image-to-video or video editing, which act as a form of constrained generation, don't they?
Yes, they do. In those cases, the source image or the original footage provides a structural guide for the model to follow.
But even with a guide, the model still has to maintain consistent changes across time.
It does. And it is important to clarify that it is not generating video through one universal frame-by-frame mechanism.
Oh, I see.
And we should also note that not every model predicts pixels only from the previous frame. It has to balance preserving the original visual anchor with generating new plausible motion throughout the entire sequence.
Here's where it gets really interesting. If editing existing video provides a structural guide, why doesn't the system just edit it frame by frame, independently?
What do you mean?
Well, if I want to change a character's shirt from cotton to leather, why not just paint the new shirt onto frame 1, then frame 2, and so on?
Because independent frame editing would cause massive visual flickering.
Really? Why is that?
If the model looked at every frame in isolation and applied the edit, the tiny mathematical variations in how it generated the new shirt would pile up instantly. The fabric would appear to boil.
Fabric boiling. That sounds awful.
It is very jarring to watch. The colors would vibrate violently, and the edges would shift back and forth.
So essentially, the model would lose track of object permanence from 1 millisecond to the next if it didn't enforce that consistency.
That is the core issue. To prevent that boiling effect, the model must balance preserving the source structure with applying the new transformation consistently over time.
It has to enforce temporal consistency.
Yes, and enforcing that consistency, making sure frame 50 logically agrees with frame 1 while applying a change, is computationally very heavy.
Which perfectly transitions us into the physical realities of running these systems. We all know the heavy lifting happens during the initial training run, but people often forget just how demanding it is to actually use the tools.
Yes, there is a big difference between building the model and actively using it.
When you hit send on a prompt or ask for a video edit, the meter is running live, requiring massive memory movement just to generate that single response.
We really need to distinguish between training and inference here. Training is the intensive, upfront process that shapes the model's weights and patterns. Inference is the live, real-time computation used to process your specific prompts and generate outputs.
And inference requires physical resources. It needs hardware, memory bandwidth, and energy. Though we should emphasize that not every AI system requires a massive, warehouse-sized data center.
That is a common misconception. Smaller, highly optimized models may run efficiently on your local devices, like a smartphone or a laptop, keeping the data and the processing entirely local.
But whether local or in the cloud, generating an answer can be fast or slow depending on a specific set of factors, right?
Yes. The speed of inference is impacted by the size of the model, the length of the output you requested, and the length of the context provided.
Plus the physical hardware running it and the current server load.
Yes. Think about server load alone. If you and 10,000 other people ask a complex question at the exact same millisecond, the physical hardware is bottlenecked.
The model has to manage its memory bandwidth, moving massive amounts of data just to calculate your next word, which slows the whole generation down.
And that doesn't even factor in extra system steps, like the model pausing to use a web search tool before responding.
Because inference is so demanding, engineers have developed fascinating efficiency techniques to make it manageable.
Yes, they have had to get very creative.
Let's look at one called Mixture of Experts, or MOE. Think of MOE like a massive library, where a guide directs you to specific aisles based on your question, rather than making you walk through every single aisle every time you ask something.
That is a highly effective way to visualize it. In an MOE architecture, a router activates selected expert components within the network rather than using every single parameter for every single token.
Now, just to be clear, these are not literal human departments.
Oh, no. They are just groupings of parameters, and it does not mean the rest of the system performs no work whatsoever, but it vastly reduces the active computation required for each specific step.
Another fascinating technique is quantisation. This involves using lower precision number formats to reduce memory use and bandwidth.
Think of quantization like measuring ingredients for a recipe. During training, the model might measure its weights with extreme precision, like a scientist measuring a chemical down to the microgram. Quantization simplifies those numbers, measuring by the teaspoon instead. The model still retains its structure, but the numbers representing its weights take up less digital space.
So it saves memory. Does it affect the quality of the output?
The effects on speed and quality depend heavily on the hardware, the implementation, the specific model, and the task at hand. Sometimes you don't notice a difference. Sometimes the output gets slightly degraded.
We also see a technique called distillation. This is where a smaller student model learns useful behaviors from a much larger teacher model.
Yes, and the goal there is to reduce the model size and the cost of inference. The student model is essentially trained on the outputs or the internal states of the teacher model.
But does that mean the smaller model is just naturally worse at everything?
It is important to note that a distilled model does not inevitably fail at complex reasoning.
Oh, really?
The capability it retains depends entirely on the training target and the specific task it was designed to handle. A distilled model might perfectly mimic the teacher's tone in writing an email, even if it loses some of the multi-step logical reasoning the teacher used to structure its arguments.
If we connect this to the bigger picture.
Well, if we connect this to the bigger picture, efficiency isn't just about making the AI smarter, it's an engineering necessity.
Yeah, to make these highly capable models usable in the real world without exhausting computational resources.
Or burning through unmanageable amounts of energy.
And those computational limits are exactly why models struggle when a conversation goes on too long. That brings us to how AI handles context, state, memory, and something called the KV cache.
This is an area where users get very confused.
Yeah, when you use a chatbot, it feels like it is getting to know you. But we need to carefully distinguish between the different types of state and memory at play.
Yes, human intuition fails us here. First, there is model training, which is a permanent change to the model's fundamental weights.
That's the baseline.
Then there is active context, which is the current window of text the model is looking at right now. There is temporary session state.
And finally, there is product-level save memory. That's where the application actively saves facts about you outside the model.
Yes. We have to remember that using earlier conversation text as context is not the same as human-like memory.
The model is not learning your conversation permanently in real time. It is simply reading the active context you provide. And in long conversations, earlier details have to compete with newer instructions.
As the context window fills up, those older instructions face immense pressure. They might receive less useful computational attention.
Or they might be truncated entirely to fit the limits of the window.
Or they might be compressed. Or they might be affected by the application's specific context management system. Old instructions do not always fade through one universal mechanism, but they are constantly competing for the model's focus.
To manage the incredibly heavy computational load of reading all that text over and over for every single new word, the system uses the KV cache. The KV cache stores key and value representations from earlier tokens.
It is a vital part of making these systems fast enough to use.
So what does this all mean? Think of the KV cache like keeping organized, highly detailed notes from earlier chapters of a book you're summarizing, rather than having to reread the entire book from page 1 every time you want to write a new sentence.
That is a helpful analogy. It acts as a computational shortcut that reduces repeated work during generation.
But even with those notes, the new token must still interact with that cached context to make sure the sentence logically makes sense.
This raises an important question about the illusion of memory. The AI isn't learning about the user permanently during a chat, it's merely juggling temporary active context.
Which is precisely why it can seem incredibly sharp, referencing a tiny detail from 2 messages ago, and then strangely forgetful just moments later.
Losing a core instruction from the very beginning of the exact same conversation, it is constantly balancing the recency and salience of the tokens within its active window, aided by that cache.
It is a remarkable technical achievement, but it is fundamentally different from human cognition, which brings our entire discussion together, I think.
Yes, it really connects all the pieces.
We have looked at how text is predicted token by token, leading to varying paths and cautious wording. We explored how video is generated across space and time, requiring immense temporal consistency to keep a scene from drifting.
We broke down how inference demands physical resources, driving the need for efficiency techniques like MOE, quantization, and distillation.
And finally, we saw how the KV cache and context limits create a temporary, fragile illusion of memory.
The reality of AI behavior is driven by those underlying engineering constraints, and that leads us to the most crucial takeaway of this entire guide.
Which
Fluent text, convincing motion, and apparent memory should not be treated as proof of verified truth, permanent understanding, or stable continuity. They are simply outputs of prediction-based systems.
If you want to explore these specific concepts further, check out the complete April 2026 guide and find many more plain English explanations at howaimodelswork.com. It is an incredible resource for seeing past the surface of these technologies.
It really helps demystify how these tools are actually functioning.
As we wrap up today, I want to leave you with a final thought to mull over. As these systems get faster, as efficiency techniques advance, and as the generation becomes perfectly smooth on the surface, how will we train our human brains to look for the invisible limits of prediction that are still operating beneath the surface?
That is something we will all have to figure out.
Thank you for listening, and keep questioning what you see.